Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll continue with some numerical examples on torsion of shafts. Let us start with the first example. A hollow shaft with a diameter ratio of 0.8 is to transmit 120 kW at 100 rpm. The maximum shear stress is limited to 52 megapascal and the angular twist is limited to 3 degree in a shaft length of 4 meter. Find the minimum outer and inner diameters of the shaft required. G is equal to 75 kilonewton per mm square. So this is a hollow shaft with a diameter ratio of 0.8. So diameter ratio 0.8 means di by d naught. So di by d naught is 0.8. It has to transmit 120 kilowatt at 100 rpm and you have two constraints. Shear stress should be limited to 52 megapascal and angular twist should be limited to 3 degree in a shaft length of 4 meter. Modulus of rigidity of the shaft is given. Given data is P is 120 kilowatt, N is 100 rpm, tau max is 52 megapascal, theta is 3 degree in a shaft length of 4 meter or 4000 mm. Diameter ratio is taken as K, which is 0.8. It should be dA by d naught. It cannot be d naught by dA. D naught by dA means it should be greater than 1. So anything diameter ratio less than 1 is dA by d naught. Modulus of rigidity 75 kilonewton per mm square. Kilo is 10 raised to 3. So 75 into 10 raised to 3 Newton per mm square. So its inside diameter dA divided by d naught is 0.8. Mean torque transmitted can be found out by this equation. P by 2 pi n into 6 into 10 raised to 7 Newton mm. P is 120 and n is 100. So substituting that you will get 11.459 into 10 raised to 6 Newton mm. So this is the mean torque transmitted and you are not given any other constraint, that is maximum torque condition is not given. So the mean torque itself can be used to find out the dimensions of the shaft. Now first we'll go for the shear stress consideration. It's a hollow shaft with outer diameter d naught and inside diameter di. On the outside surface the shear stress should be limited to 52 megapascal. Inside surface will be having minimum stress, not zero stress. If it's a solid shaft, minimum is going to be 0 at the center. But when it is a hollow shaft, you will have minimum value of hoop stress on the inner walls and maximum will be on the outer walls. So this maximum value on the outer surface should be limited to 52 megapascal. Now T is J by R into tau max. And for a hollow shaft, J by R we know it is pi by 16 d naught cube into 1 minus k to the power of 4. That is J by R or polar modulus. So polar modulus into tau max. T is equal to polar modulus of hollow shaft into tau max. Now T you can substitute this mean torque pi by 16 into d naught cube into 1 minus K values diameter ratio 0.8 and maximum shear stress is 52. By substituting that you will get d naught as 123.877 mm. So once you get d naught you can multiply this with 0.8, so which will give the inside diameter as 99.101 mm. And these are the outer and inner diameters. Outer diameter and inner diameter for satisfying this maximum shear stress 52 megapascal while transmitting 120 kilowatt at 100 rpm. So this is only considering the shear stress we are getting these diameters, but we need to check the angular twist also. So we have another condition: angular twist should not exceed 3 degree in a shaft length of 4 meter. So for that you have to use part of the torsion equation. T by J is equal to G theta by L, or J is TL by G theta Now torque is known, length is 4 meter or 4000 mm, and G value is given 75 into 10 raised to 3 Newton per mm square. Angular twist is 3 degree, so converted into radians 3 into pi by 180, and this 3 degree in 4 meter length. So this rotation is 3 degree. 3 degree is the outer diameter, inner diameter. Now the angular twist overall, the shaft will rotate by 3 degree in a shaft length of 4 meter. The shaft can rotate, and overall the shaft can rotate relative to the other end. It can rotate by 3 degree in a shaft length of 4 meter while transmitting the given torque or this mean torque. By solving this, you are getting the polar moment of inertia, and since this is a hollow shaft, polar moment of inertia is 5 by 32 into t naught to the power of 4 minus t8 to the power of 4, or 5 by 32 into t naught to the power of 4 into 1 minus k to the power of 4, because if you take d naught to the power of 4 outside, you will get 1 here, and you get ti to the power of 4 divided by d naught to the power of 4, or di by d naught to the power of 4, which is k to the power of 4. So taking d naught to the power of 4 outside, you are getting in this form, where k is di by d naught. Okay. Now k we know this 0.8, diameter ratio 0.8. So we can substitute that and find out the diameter of the shaft. So outer diameter we will get as 119.124 mm. Once you get the outer diameter, you can multiply that with the 0.8, which will give the inside diameter, and you will get the inside diameter as 95.299 mm. So this is another solution to satisfy the angular twist. So it is only satisfying the angular twist, whereas the previous solution was satisfying only the maximum shear stress. Now both should be satisfied. To satisfy both, let us check the values. This is a maximum diameter 119.124. Diameter can be more than this, but not less than this. Okay, this is a minimum required to satisfy the angular twist constraint. So you cannot go the diameter below this. Now for shear stress consideration, minimum outer diameter is 123.877. So you cannot go below this. So this second value is not possible, because if you use this value, shear stress will go beyond 52 megapascal. Okay, it goes beyond 52 megapascal, because for 52 megapascal we need, this is the diameter required. So if you use a diameter less than this, shear stress will increase. So second solution is not possible. So you have to take this first solution as the minimum diameters of the shaft. So you can select the minimum diameters of the shaft required as 123.877 and corresponding DI value 99.101 mm. So this will satisfy both the constraints. While transmitting that power, shear stress, maximum shear stress will be 52 megapascal, and since we have used diameter more than what is required for satisfying the angular twist constraint, angular twist will be less than 3 degree in a shaft length of 4 meter. So both will be simultaneously satisfied. Angular twist less is okay, less than what is the maximum restricted will be okay. So we have to use these diameters for the shaft to satisfy both the conditions. Now let us work out another example. A solid shaft is to transmit 192 kilowatt at 450 rpm. Taking allowable shear stress for the shaft material as 70 megapascal, find the diameter of the solid shaft. What percentage of saving in weight could be obtained if the shaft were to be replaced by a hollow shaft with a diameter ratio 0.8 for the same torsional strength? We have a solid shaft which transmits 192 kilowatt at 450 rpm. Now you have to find out the diameter of the solid shaft to transmit this power, keeping the maximum shear stress to 70 megapascal. So you can use the equation torque is equal to IP into tau max, or IP is pi by 16 d cube. So torque is equal to pi by 16 d cube into tau max. You can find out the diameter of the shaft. From the power transmitted and speed, you can find out the torque, and you can find out the diameter of the solid shaft to transmit this power, keeping the maximum shear stress 70 megapascal. Now you want to replace this by a hollow shaft with a diameter ratio 0.8, and we are replacing the shaft for the same torsional strength. When you replace it for the same torsional strength, it should be able to transmit the same power at this speed, keeping the maximum shear stress same. So while transmitting this power, the shaft should have the same maximum shear stress. Shear stress should not exceed 70 megapascal. So that is the meaning of same torsional strength. It should be able to transmit the same power, keeping the maximum shear stress to the same value as the previous shaft. So you are replacing by hollow shaft with the same material for the same torsional strength, and you have to find out how much material you are saving when you are replacing it for the same torsional strength. Now these are the data given. Power transmitted is 192 kilowatt, speed is 450 rpm, maximum shear stress is 70 megapascal, diameter ratio of the replaced shaft is 0.8. So these are the data given for a solid shaft. You can use this equation. From this power and speed, you can find out the torque transmitted, and then once you get the torque transmitted, you know the maximum shear stress 70 megapascal. So use this equation, you can find out the diameter of the solid shaft to transmit this power. After getting the diameter of the solid shaft, now you want to replace this solid shaft by a hollow shaft with the diameter ratio 0.8. That means d0 is 0.8 di. Power transmitted of solid shaft and hollow shaft should be same, and maximum shear stress, because we are replacing it for the same torsional strength, maximum shear stress induced in both the shafts, solid and hollow shafts, while transmitting this power should be same. Now the replacement is for the same torsional strength, so that means hollow shaft also should transmit the same torque as solid shaft, keeping the maximum shear stress same. These values should be same, that is 70 megapascal. So torque is same, maximum shear stress is same, so that means set P values, polar modulus of both the shafts should be same. Okay, so this is a polar modulus should be same. Let us find out the diameter of the solid shaft to transmit this power. Okay. So to find out that, you have to find out the torque transmitted by the shaft. So mean torque is given by P by 2 pi n into 6 into 10 raised to 7 Newton mm. Power should be in kilowatt only. So 192 kilowatt, speed 450 rpm. Substituting this, you get the mean torque transmitted by the shaft as 4.0744 into 10 raised to 6 Newton mm. After getting this T mean, this average torque itself can be taken as a torque transmitted by the shaft. So torque transmitted is J by R into tau max. So J by R, which is set P, polar modulus, it is pi by 16 d cube for a solid shaft into tau max. Tau max is known, torque is known, torque we calculated, so we have substituted the torque, and tau max is 70. So from this you can solve for d. Diameter of the solid shaft to transmit this power is 66.677 mm. So we should have a diameter of minimum diameter of this 66.677 to transmit 192 kilowatt at 450 rpm keeping the maximum shear stress 70 megapascal. Now we are going to replace this solid shaft by a hollow shaft with a diameter ratio 0.8. So I am just replacing this by a hollow shaft which should also transmit the same torque and keeping the maximum shear stress same. So that means ZP values of both the shafts should be same. Okay, ZP of hollow shaft should be equal to ZP of solid shaft. Now ZP of hollow shaft, you know, pi by 16 d naught cube into 1 minus k to the power of 4 is equal to solid shaft. We have pi by 16 d cube. Now pi by 16 cancels. D naught cube into 1 minus k to the power of 4 is equal to d cube. And we already got d, so you can substitute for d, and the diameter ratio of the replaced shaft is 0.8. So substituting that, you can find out the outside diameter. So outside diameter is 79.48. So replaced shaft should have a external diameter 79.48 mm. So once you get the external diameter, you can multiply with the diameter ratio to get the internal diameter. So internal diameter is 63.584 mm. So these are the diameters of the replaced shaft. Now, if you are using these diameters as the external and internal diameters, the replaced shaft also can transmit the same torque, keeping the maximum shear stress to 70 megapascal. Now question is to find out the percentage saving in material. So while replacing this shaft by making it hollow, you are saving some material. Okay, even though external diameter has increased, earlier it was 66.677, the external diameter is more, but some interior portion is removed. Even by making it hollow with less material, it's able to transmit the same torque, because the internal area is not contributing much to resist the torque, because you know the shear stress induced on the interior portion of the solid shaft is less, because maximum shear stress is induced on the surface, and the major part of the torque is resisted by the external layers than the internal layers. Internal layers, less amount of resistance is offered while transmitting the torque. So even if you remove that internal portion, and the removed internal portion, if you add to the external surface, that will increase the torsional strength of the shaft. So with the less amount of material, you can make a hollow shaft which will be able to transmit the same torque. Now we have to find out the saving in material by replacing this with the hollow shaft. So percentage saving in material you can find out as, so weight of solid shaft minus weight of hollow shaft, this will give the saving in weight, divided by initial weight, that is weight of solid shaft, that into 100, that will give the percentage saving in material. Since the materials are same, weights are proportional to the area of cross section, because area of cross section into length into specific weight will give the weight. Since the length and the specific weight are same for a solid and hollow shaft, the length into specific weight will cancel in the numerator and denominator. So AS minus AS by AS into 100 will give the percentage saving in material. So AS is pi by 4 into d square. Area of cross section of hollow shaft is pi by 4 into d naught square minus di square, divided by pi by 4 into d square. Pi by 4 can be taken outside in the numerator, and denominator you have pi by 4, so pi by 4 cancels, so you get d square minus d naught square minus di square divided by d square into 100. So we already know that d naught di, so you can substitute that values and find out the percentage saving in material. So you get the percentage saving in material as 48.85% in this case. When you replace the solid shaft by a hollow shaft with a diameter ratio 0.8, in this case we are getting a percentage saving of 48.85%. So we are replacing it for the same torsional strength. That means both while transmitting the same torque will have the same maximum shear stress. Angular twists can be different, but in fact the angular twist in the replaced shaft will be less when you are replacing for the same torsional strength. So even the angular twist will be less in the replaced shaft while replacing it for the same torsional strength. That's all for today. Thank you for watching.